I have a question for the audience because I don't have quite enough slides, perhaps, although I can talk a lot. So here's the question. How many people in the room understand the difference between lithosphere and asthenosphere? Oh, dear. Okay, and crust and mantle. More people understand crust and mantle. Okay, Yuri and Nestor, we have some work to do here. But I'm not going to address this. But as a geologist, I love lithosphere and asthenosphere. Okay, this is a great title. Is oil and gas drilling and well competence needed for geothermal resource extraction? And apologies for the next slide. It's a little bit informal. That's not what I want to do. Yep. And we'll address some of this. Just my hunch here. But I think there's a lot of work for the entire labor value chain without that much retraining. And we don't quite find that with wind and batteries. Okay. Start here. On the left, it's from a Technisk Ukeblad review of this 1997 patent for the Ula field. And if you want to know about Ula, I think that you should talk to Anna Ella over there. In fact, I tried to get her to give this presentation, but, well. So, not a new idea. 10 megawatts, SINTEF stamp of approval from circulating water, and it didn't catch on. So, we're going to come back to this idea that's on your right, but it's basically that we have a platform or a floating rig, and we have boreholes, and we have various aquifers at different depths, and we have, say, oil or gas in traps, and a bunch of wells which are not used anymore, out of use. So, to skip around a little bit, maybe a year ago, with the help of EJEC, Philippe Dumas, is he here? Not yet. But he set it up so that Turbuden, the Italian turbine company, geothermal company, whole plants, would do some calculations for us. And they said for the Kristen field, this is just from the water cut, not using the oil, but there's much more water than oil and gas from both these fields. For Kristen, high temperature, high pressure field, 160-degree fluids in the reservoir, we could generate 1 megawatt of electricity. Of course, there's a lot of heat, but essentially it's in the low 10%, maybe 13% efficiency. For Ecofisk, if we take the water cut from the entire field, 7 megawatts. And these are gross. This is if we have to pump to circulate the fluids. This is saying oil and gas pays for everything. We just take the water and generate electricity for us. These are really low. I mean, this is not going to be of interest. But if you think back to the previous slide, I'm not sure how we go backwards here.
You can use the arrows on the keyboard.
Yeah, okay. It's a small output, but why rely on the water cut? Why rely on the oil and the water? Why not make it a proper geothermal project and take and use existing wells Or if it's economical, drill new wells. And one thing about petroleum, using petroleum reservoirs, is that this last one, gas lift, there is, for example, well, there are examples all over the world, but if there is some gas in the reservoir dissolved in the water, even if it's CO2, we'll hope it's not H2S, it will lift. Your electric pumping costs are much lower if the water is lifted. Okay. So, what we want to consider is repurposing out-of-use wells, which might be out of use because they're producers and they've been flooded. In other words, the gas oil or the gas water or the oil water contact has come up above them, or that the base of the oil was down here, but now this is all water here, for example. So these could be repurposed. Typically, they're completed with maybe a 6-inch diameter, 5 or 6 inch, whereas for geothermal, typically it's a 9-inch or larger borehole. But if you take for the cross-sectional area, if you take three 6-inch wells, you get the equivalent of a 9-inch well. 4, sorry. And maybe with friction 5. So these can be recompleted. You could make this a closed loop system with multilaterals making fences between. But if the reservoir properties are good, you can just have a conventional doublet. Well understood because there are lots of samples of the formation fluids, and the injectivity is well known from the oil production. Okay, we can use these fluids directly. If you have a new build platform, you can plan to use the fluids for heating on the platform, the space heating and some other low temperature applications. You can save 15 or 20% on your electricity bills. If you have land power or offshore wind, you need 20% less electricity. Process heat. Electrolyzers for hydrogen and the process of making ammonia require heat. Quite different heat. Maybe 80 degrees is good for an electrolyzer. That's the temperature of the reservoirs in many fields. It's 200 or so for ammonia. But we'll come back to that. There is a high temperature, high pressure field where if you drill 300 meters lower, you get to 200 degrees. Okay. Hydrogen electrolyzers need very clean water. You can't put seawater in them. You'd have to desalinate first. You can use, from higher temperature reservoirs, you can either flash the water, as in let it boil, make steam, turn a turbine, make electricity, and then collect the condensed water, fresh, good for much cleaner than seawater. And you could also do this from a lower temperature reservoir, which is still above boiling. So it integrates. The point here is we're integrating with other green energy production and maybe making it cheaper to use offshore wind to make hydrogen for post-oil energy hub use of the existing infrastructure. For generating electricity, we want to be above 110. That's not so much of a problem, but that's not very efficient use of the fluids. If we can get hotter fluids, it's more efficient. I mentioned these before, but 10 megawatts for Ekofisk would take about 1,000 cubic meters per hour. That's much more than the, that requires a number of wells. Another question is, do we bring the fluids up to the platform? It would need an insulated riser, and the complaint is always there's no space on the platform. Maybe if offshore geothermal got from TRL 4, because it hasn't been tried yet, to TRL 8 or 9, it would be considered reliable enough so that you could just get rid of the gas turbines and use that space. But one thing about these, about geothermal is you can, with the ORCs, you can split the system. You can have the heavy heat exchanger low, and you can put the actual turbine, which is much lighter, in a different space. The gas turbines have to be all in one space. Okay. Platform or seafloor? What if we put it on the seafloor? This is a demo we'd like to do, so if anyone wants to help make a JIP and do the demo, I think that would be great. When I got off the bus, the Fleabus, yesterday, probably on the far side of this building, I saw this white steel structure with sort of towers and a very thick middle. I think this is a wellhead. But if we had a wellhead in the Stavanger area just to test an underwater ORC, I think that would be great. We have a company that makes small ORCs, which has already done the engineering to encapsulate it. For 50 or 100 meters, that's easy, they say. 300 meters, that might be a bit difficult. So then, the last one is, there is a French company, I keep forgetting their name. It basically means energy storage, rock energy storage. And then next to the EGS test site in Nevada in the US, the Forge test site, there's the company Fervo, which has done essentially the same thing. And this thing is, you pump fluid into the reservoir, and you basically elastically expand the reservoir, creating some fractures, but not a lot, and you store energy hydraulically. And you can use this hydraulic energy because you've lifted the rock above in a sealed reservoir. This is done actually in granite and gneiss in the US Nevada example. It produces the fluids when you open the valves for days to weeks. Yeah. So we could discuss that later. Okay, the last thing is a couple of reservoir temperature plots. I'm going to show you three versions of this graph, but what I want to say is this is organized by geothermal gradient for oil fields on the Norwegian shelf. it goes from a high of about 53 down to the average of 35. Okay, so that's the way this table is organized by geothermal gradient. Now we're going to move one to the right, and we're going to look at the reservoir temperatures. So one thing you can see immediately is where the geothermal gradient is low, which is at the bottom, there we have the highest temperatures in many cases. High temperature, high pressure fields are deep, that's why they're high pressure. But they still have to be cold enough so there's oil, or the gas hasn't all burnt off. Okay, so here, the depth of the reservoirs is in this table, this column, and the temperature is here. Green where it's too low for electricity, red where it's good for electricity. Okay? So the point is, all of the reservoirs are great for direct heating. Some of them are good for electricity. Now we're going to, this is real. Here is a hypothesis. So we take the geothermal gradient and we say, how far do we have to go? How deep do we have to go? But also, how far below the reservoir which has been drilled to get 200 degrees? This is why I sent you a version 2, but too late. Okay, so 300 meters below Tambar, below the Tambar Reservoir, 200 degrees. Of course, the depth is 4,400 meters, 4,430. So if you're going to drill a 9-inch hole down there, that's quite an investment, even if you can somehow use the existing 5-inch or 6-inch holes. So I'm going to stop here. But these are maybe an area we could discuss later. How do we put together some projects to address this? And is it going to be, is a JIP, a joint industry program, the best? Is it going to be research council money or a combination? And that's it. So thanks for listening. And I think that the future is hot, especially if we do this. It's very hot for reusing all of the Norwegian competence. Atle from Schlumberger in the back, and Roberts and Tate from Schlumberger have pointed out that this has not been done anywhere in the world, offshore geothermal. At the same time, we've tried to get all the oil companies in Norway, both partners and operators, to bite. They're all sitting on the fence.
Yeah. Walter is like me, really likes to talk. So thanks a lot.
It's a competition.